This video is a continuation of Kinematics Part 1, specifically focusing on the motion graphs. So they say a picture is worth 1,000 words. Well, so is a motion graph. Once you learn how to read a motion graph, you can tell at a glance if an object is moving away from you, towards you, moving at a constant speed, speeding up, slowing down, and much, much more. So let's start by imagining you're standing on the side of the road and a car approaches you from behind, traveling at a constant speed. The car then passes you and disappears off into the distance. To graph the motion of the car, you have to start with data. So you're going to use a stopwatch and markers on the side of the road every 10 meters. You then record the car's distance from you at every second. Negative displacements show that the car was behind you. Positive displacements show that the car was in front of you. You are the origin point. So when the car passes you, that means the car is 0 meters away from you. So now let's go ahead, and then the negative sign and positive signs just are there to show that the car is on one side of you or the other. So let's go ahead and graph the data. If we graph the data, we start with the car behind you, and then we have the car in front of you. Negative, positive on our displacements. The slope of the the slope of the displacement versus time graph is telling us the object's velocity. In this case, the line is straight, and that means that the slope and hence the velocity is constant for this car. We can calculate that slope as the rise over run, which is we usually do that as the change in y over the change in x, but the y-axis has an x, so it's the change in x is our change in y. The x-axis is going to be our change in time, and so that's what we have here. So the equation is the change in position divided by the change in time. And that would be the final position minus the initial position divided by a final time minus an initial time. So I'm just going to pick 2 points on the line and go ahead and calculate the slope. In this case, what we have is a velocity of 10 meters per second, and that's going to be a positive velocity, which means the car's velocity is in the positive direction. Here's another graph that describes the motion of another car you see while standing along the side of the road. Think for a moment, can you describe the motion of this car? If you said that this car approached you from in front and then passed you by, you were correct. It is also true that this car is traveling at a constant velocity. The graph is a straight line. But is it the same constant velocity the last car had? If it is the same velocity, if the slope of the graph line is the same. So we can calculate our slope, picking 2 points, plugging them in. This time we get a slope of negative 9 meters per second. So if we're trying to compare the slopes, we're looking at the magnitudes. And we can see that the second car is traveling a bit slower than the first one. Its velocity is 9 meters per second compared to 10. The negative sign just shows that it's in the opposite direction of the first car. And you can see that very easily glancing at the two graphs. The negative sign on the second car's velocity means that it was traveling in the opposite direction of the first car. It's much easier to compare the motions of the two cars when you graph those motions on the same set of axes. So here it's easier to see that the slopes are not quite the same. Of particular interest is the center section of the graph, the A, B, and C points. Can you figure out what is happening at each of the labeled points, A, B, and C? Point A is where the first car that came from behind you passes you. It is at the origin line, which means it is 0 meters from you. Point B is where the two cars pass each other. And that's going to be in front of you because it's on the positive side of the displacement. Point C is where the second car that came from in front of you passes you. That is where it is, again, at the origin, at the 0 line, which is where you are. Where the graph lines intersect, the horizontal axis is where the object passes the observer. That is 0 meters from the observer. Where the graph lines intersect each other is where the objects pass each other. They're at the same position from the observer. When the two cars are moving in the same direction, it's much easier to compare their speeds, both in real life and on a graph. So I can calculate the speed of car 1. Finding the slope, it will be 10 meters per second. For car 2, it's going to be 6 meters per second. The less steep the slope, the slower the car. The steeper the slope, the faster the object is moving. The slopes of their graph lines are obviously different. The slope for car 1 is steeper, therefore it must be going faster. All right, here's another situation. A black car is traveling along the highway at constant velocity. A blue car follows along behind it at the same velocity. And here's our data. The black car then pulls to the side of the road and stops. The blue car pulls up behind it and also stops. First, if we look at the data table that describes their motion, first we're going to look at the data table that describes their motion, then we're going to graph it. So if you look at the data table, you can see here the car does not change its position, so this must be where it stopped. Here you have a constant change in position. Here we have a constant change in position, and then that change in position stops. So if we graph the data, this is what it's going to look like. So when we interpret the graph lines are parallel. That means both cars have the same constant velocity because the slopes for both of those lines are going to be the same. While moving, the distance separating the cars remains constant at 10 meters. You can tell when the cars are motionless because the slope of their graph lines is 0, meaning 0 velocity. When parked, the distance separating the car is now only 5 meters. How about this graph? What is different about this graph? As before, the blue car followed the black car while traveling along the highway at constant velocity. Just as before, the black car pulled over and stopped. What is different is that this time the blue car passed the black car and then pulled over to stop in front of it. We know this because in the end, the blue car is farther out in front, farther away from the observer. So in the end, the blue car's displacement is greater, starting at -10, ending at +35. The blue car passes the black car right here. That is where their positions were the same. All right, here's another graph. Your friend just bought a new motorcycle and wants to show it off for you. Look at the graph below and see if you can describe the motion of your friend and his new machine. From A to B, your friend is going away from you at a constant velocity. From B to C, your friend has stopped moving. And then from C to D, your friend is returning to you. Your friend's displacement, in this case, would be 0. He ended up at the exact same distance from you that he started. Now, you can calculate the slope as well. He left you with a speed of 10 meters per second. He stopped, and then he returned with a velocity of -6 meters per second.